Good morning, Abstract Algebra. This is our very first live streamed problem-solving session of the spring semester, so I'm very happy to join you here today. Welcome to my home office. It's a little bit less pretty than my office is on Bridgewater's campus. But the purpose of today's live session is to get us some more exposure to the problem-solving process in abstract algebra. So we're just right now sort of at the end of working our way through topic number 2, which is the definition and basic properties of groups in abstract algebra. Groups are the very first abstract algebra structure that we learn about. And it's kind of surprising once we get through the 4 properties that characterize what a group is: the associative property, the closure property, the identity property, and the inverse property. Just those 4 things. What's surprising to me, at least, is just how much mileage we get out of those 4 simple properties. That there is such a wide variety of different mathematical structures that have those 4 properties and look very different from one another is the first thing that's startling to me. And the second thing is that we're going to spend our whole rest of the semester chasing down just a few of the properties that groups have that can help us to compare one group to another. So really, the big question that we want to answer together in our first semester algebra course, thinking about the theory of groups, is how can we tell different groups apart from one another? And the sub-question, I suppose, is how can we tell that 2 groups are in fact the same? What does the same even mean? And it's actually going to take us all semester just to come up with a brief classification of what are the different groups that can exist out in the wild. And we're only going to be able to answer that question for groups that are finite and groups that are abelian. So we actually are going to need both of those 2 things to be true: that our group only has a finite number of elements and that its operation satisfies the commutative property. If we can have those 2 things, then the apex of our course, the very last thing we do, is going to be to come up with a classification, to be able to write down all the different structures that a finite abelian group may have, depending on how many elements that it has in the group. But that's a pretty long way off. Our job right now is to figure out what can we say just from knowing the basic definitions and basic properties of a group. How can we, first of all, apply those definitions to assess whether or not a given structure is a group? And then secondly, how do we grow accustomed to the process of discovering and communicating a proof in this area of group theory? But the work that we do on that right now is going to pay dividends as we go along. So I should say, before we dig in today, if you're currently taking my class and are watching this live, feel free to participate by contributing your questions and comments into our Slack channel in the doctor's office board. There's a place for you to do so. I'm monitoring that as we go, so if you have questions, drop them in and I can respond to them. Of course, this becomes a YouTube video after the fact. If you're watching this on YouTube, you can use the timestamps that are in the video description below to jump to different parts of the video. So this is going to be an hour-long session, but if you just want to go to particular problems that we worked on, you can click on the timestamps and you can jump straight to them. So far, before our session today, I had 3 problems were contributed to us, and let's take a look at what those 3 were. The first question that people wanted to hear about was about the associative property. So how do we come up with a way to demonstrate that a given operation satisfies the associative property without explicitly checking every possible combination of 3 elements that we could have within a group, because that workload grows very quickly as the number of elements in a group gets bigger. So that's the first thing I want to think about, and I'm going to do that by thinking about the problem which in our homework set is listed as problem number 3. So those numbers relate to the numbers on this preparation page right here. So if we jump into there, our problem 3 is problem 7 in Judson's exercise set. So that's the first one I want to talk about. The second one is listed as our problem number 5 and is Judson's problem number 15. And that relates to the question of whether or not a group having 6 elements must or might not be an abelian group. So do we get the commutative property automatically in any group that has 6 elements in it? And the third problem is number 7 on our exercise set, which is 25, and Judson's exercise set, which is a more mechanical problem, asking us to figure out how to take the power of what we call a conjugate element inside of a group. So those are the 3 that I have on my list right now, but if another one comes up while you're watching, again, if you're my current student, drop that into the Slack Doctor's Office channel. If you're watching this live on Twitch and you're not a part of our class this semester, you can also drop questions into the Twitch chat. I will prioritize any questions coming from my current students through Slack first, but if you're watching this via Twitch and joining us today and are not a part of my class this semester, feel free to interact via the Twitch chat because I'm watching both of those at the same time. So let's go ahead and get started right away with that first question about associativity. So this question came from the question of whether or not the operation in a group is associative came from one of my current students. And it's something that, I'll be honest, we don't spend a lot of time really fretting about. Even though associativity is kind of a big deal, we do need all of our operations in group theory to be associative. One of the things that I always tell my students is that this is usually not, if something is not going to be a group, it's usually not associativity that's the thing that fails. Most operations that are sensible in mathematics, that we define in a sensible way, end up being associative because most of those operations are defined in terms of the composition of functions. And composition of functions is kind of the prototype for an associative operation. So anything we define in terms of composition of functions will end up being an associative operation. But what I wanted to do is provide a chance for us to look together at an operation that's not associative, or so that may or may not be associative, and look at kind of what a proof whether or not that operation is associative might look like. So this comes from Judson's exercise set number 7. And so the question reads, here's a set. It's the set of all real numbers except for -1. And we define a binary operation on this set in a curious way. Right? We define an operation called star, and the star takes the sum of 2 numbers and adds the product of those 2 numbers. So it's the sum plus the product. And the question is, does this form a group? And the question, actually, Judson's question, gives away the answer. That in fact, with the operation a star b equals this thing, the set of all real numbers with the exception of -1 does in fact form a group. Not only does it form a group, that group actually turns out to be an abelian group. Okay? So the answer is sort of given to us out of the chute. So rather than go through in detail all of the properties we would need to check, because we would need to check all 4 group properties plus a 5th because of the word abelian sitting right here. Maybe I'll just use this as an example to look at the associative property, and then also maybe we'll talk about verifying the abelian element, which is going to be, I think, a little bit more straightforward. So let's go ahead and get started. All right, so if I want to check associativity, let's do that bit first. Is star an associative operation? And again, I mean, the answer is kind of given to us in the problem here because it says prove that this thing is a group. That must mean that we are going to answer this question in the affirmative. And what I actually want to do together is I want to write a proof of this, because we cannot possibly get too much practice with actually figuring out how to write a proof for one of these kinds of assertions. So because I want to write a proof, the first thing I'm going to do is I'm going to drop a napkin down on the table, and we're going to use this napkin as our way to get started brainstorming the sort of the calculations that are going to go into the proof that we're about to write. So the first question that we would have is, what is the associative property? What does an associative operation satisfy? So the definition of associative. The definition of associative says, for all, so don't leave out these quantifiers, for all x, y, and z that belong to the set of elements of my group, and here the set of elements of my group is being called S. So for all x, y, and z that belong to S, we need to have the following hold true. Remember, the associative property is about the relationship between the evaluation of a triple product. So I have 3 elements, and I'm trying to do x, y, and z sort of starred together, x star, y star, z. And for an associative operation, the assertion is that the order in which we evaluate either the first operation here and then the second, or the second followed by the first, that order doesn't matter. In other words, it does not matter where I put the parentheses and which of these pairs of elements we decide to combine together first, that the result needs to be the same in either case. So that's the statement of the associative property. It starts with this quantifier for all elements x, y, and z that belong to the set of elements in my group. This equation, x star y, the quantity star z, equals x star the quantity y star z. So that's what we must verify in order to verify that the associative property holds in our group. All right, so let's take this down to our napkin. So we're going to do the scratch work down here first. And then when the rubber meets the road, we're actually going to type that up into a proof also here in real time. So on my napkin, I need two things. I need the statement of my associative property, this equation that I want to be true, x star y, the quantity star z. And then maybe on another part of my napkin, I'll write the other part, x star, the quantity y star z. So these two things are the things that I want to show are they're exactly the same as one another, on the nose for all values of x, y, and z. But the issue here, of course, is that this star is the operation in my purported group. And so this star is defined by this statement up here on top. So there's a definition of the star operation that is also needs to be a part of our argument. And so there's another definition that comes to bear in this. And the definition is that A star B is the sum added to the product of these real numbers, right? So we're going to need to plug in that definition also to figure out how to simplify, or in other words, how to turn these statements about weird star operations in a group into statements about comfortable, like old pair of jeans, comfortable addition and multiplication that happens with real numbers. Because that's the only way we're going to get anywhere is by using that definition. Otherwise, we don't know what star even means. We're not going to get anywhere. So on my napkin, the first thing I'm going to do here is I'm going to simplify out these star operations into familiar operations on the real numbers, starting, as we always do, with the order of operations inside the parentheses. So x star y, if the star operator is defined this way, x star y is going to be x plus y plus xy. Right? So it's that thing, and then I'm going to star that with z. Right? So that's what I get in my first, the left-hand side of the equation that I'm trying to deduce here. And then again, using the star operation, we're going to take this thing as my a. So the role of a will now be played by this whole quantity. The role of b is going to be played by z now. And we're going to get a plus b plus a times b. X plus y plus xy quantity times z. So now I've completely converted all of my weirdo stars into comfortable, familiar arithmetic on the real numbers. Right? And just because I'm sort of running out of room on my napkin already, I'm going to simplify this product down here, and then I'm going to rewrite what we have. So because all of the arithmetic now is familiar real number arithmetic, we can take for granted things like the commutative, the associative, the distributive properties inside of the set of real numbers. And so now we can just distribute this z, and what I end up with when I do that distribution is xz plus yz plus xyz plus xyz. So that's what I get when I simplify this expression on the left-hand side of this equation that I'm trying to deduce. So this equation is going to ultimately become our burden of proof when we write the proof. But on my napkin, we're not worrying about that. We're just worrying about trying to simplify this expression as much as possible, and then simplify this expression as much as possible for us to determine whether or not they are indeed equal to one another for all values of x, y, and z. So we've completely simplified the expression on the left. Now let's worry about the expression on the right. Here we're going to start inside of these parentheses, y star z. Y star z, again, by definition of our star operation, is y plus z plus y times z, the sum plus the product. And then when I do x star that, Now the role of A is being played by X. The role of B is being played by Y plus Z plus YZ. And so we're going to get A plus B plus A times B, Y plus Z plus YZ, right? And now again, because we can take for granted the distributive, associative, commutative properties of real number arithmetic, we can distribute that x into these parentheses over here. And now what we end up with is xy plus xz plus xyz. xy plus xz plus xyz. All right, and now we've completely simplified on my napkin both of the expressions that we started with in the equation that we're trying to determine is true. Okay. All right, but what you'll quickly notice, which you may already have noticed, is that there's a lot of similarity. This x appears in both this expression and that one. Same thing with this y. This xy shows up here, and then it also shows up there. Here's a z. Here's xz. Here's yz. Here's xyz. So in fact, both of these expressions are indeed identical, right? Here's my x, here's my y. xy ends up in kind of a different spot over here, but because the addition of real numbers is commutative, we can take that for granted. It doesn't matter which spot these things end up in. We're going to get equivalent expressions either way. The z's agree. I have an xz that I'm finding in both expressions, a yz that I'm finding in both expressions, and a triple product xyz that I'm finding in both expressions. And that's it. So if I'm sitting and having an adult beverage and writing this out, I will find out, indeed, that both of these expressions are equal. And at this point, I sort of celebrate, right? If I'm a mathematician working on a new discovery and I find this on my napkin while I'm jotting it down, that's the point at which I go home and I celebrate, basically. But then when I come back to the office the next day, I come in with a coffee, as I'm doing this morning. Paul Erdős famously said that coffee is a mathematician is a machine for turning coffee into theorems. And so I come into the office the next day with my napkin crumpled up in my pocket with my result on it. And I say to myself, all right, now I actually have to communicate this. Right? I have to write down this proof in a way that someone who didn't go through the mental gymnastics that we just went through is going to be able to understand what just happened. So let's go through the process, thinking about the sort of the 4 points of performance that make an effective proof that we talked about in our class this week. And let's try and figure out how to communicate this proof in a valuable way. So what I'm going to do is I'm actually going to start a new document here. One of the things that we are going to work on together this semester is how to type mathematics. That's going to be coming down the pipe in just a couple of weeks here. And so what I want to do is use this opportunity to kind of model that process a little bit. So let's bring in our screen for writing down my proposition. So my proposition reads as follows. The operation star defined on the set of real numbers by A star B equals A plus B plus AB. The set of real numbers not equal to -1 by A star B equals A plus B plus AB. And what I want to say in my proposition is that this is an associative operation. Satisfies the associative property. All right, so now I've just typed in my proposition. Right, this is the thing that I want to show is indeed true. So I'm just tweaking a couple of things to make this look as nice as possible. Okay, so this is the proposition that we're called upon to prove here. Now let's try to write a proof. So I'm looking over here at my napkin, right, and I've gotten all of the mechanics down. But in my proof, the first thing I want to do is signal to somebody who's reading what the strategy of my proof ultimately is going to be. Right, that was our first point of performance in proofwriting this semester. And there's really nothing on my napkin that suggests that I used any kind of indirect, any sleight of hand. We didn't use mathematical induction. We didn't do anything out of the ordinary. So I would say that what we just wrote on my napkin looks like a direct proof. So let's signal to the reader that this is going to be a direct proof. And the way we'll do that is by remembering that the associative property has this universal quantifier, this for all, sitting inside of it. And anytime there's a universal quantifier, there's implicitly an if-then relationship that's there. So another way to understand what the definition is that we're ultimately trying to prove here, I'm going to write this and then I'm going to erase it, but I'm going to write it in other words. Another way to think about what this is saying is that there's an implicit if A and B are real numbers that are not equal to -1, then we must have, sorry, not A and B. What I actually wanted are X, Y, and Z here, because again, we're working off that definition of the associative property. Then X star Y star Z must be equal to X star quantity Y star Z. Whoops. Never type in front of an audience, even when that audience is virtual, as it is today. All right, so here is kind of what this universal quantifier is doing for us, right? It turns it into this if-then statement. If X, Y, and Z are real numbers that are not equal to -1, then X star, the quantity Y star Z, needs to agree with the quantity X star Y star Z. All right, just want to add in a little bit of spacing here. All right, so it's this if-then that comes out of our universal quantifier that sort of is how I'm going to signal my proof here. And so because it's a direct proof, the first thing I'm going to do is assume the hypothesis. So assume that X, Y, and Z are real numbers that are not equal to -1. And again, I'm kind of fixing my notation here on the fly. Here we go. All right, and so I'm going to do that by bringing X, Y, and Z into existence by using a let statement. So let X, Y, and Z belong to the set of real numbers, but not equal to -1. So this proof, by the way, is not actually going to give us an opportunity to see why it's important for the X, Y, and Z to not be equal to -1. But if we were to do the full proof that this is in fact a group, we would actually see why that's an important stipulation. All right, so I'm signaling to the reader that this is a direct proof by bringing X, Y, and Z into existence, satisfying the hypothesis. Now I'm going to state our burden of proof. We wish to show that. And then what we're wishing to show is this the consequent, the conclusion part of this if-then statement, right? So this first line that I wrote in my proof is doing two things. It's signaling the strategy to the reader, and it's also providing a burden of proof. We wish to show that X star Y star Z is equal to X star the quantity Y star Z. And with that, I'm going to take out that line that I wrote before the proof. Right? So far, so good. Now, how are we going to prove this? Well, we have the work over here on our napkin, right? But what we don't want to do is we don't want to just write down this equation in our proof as though we're asserting that equation is true. As the authors of this proof, we have to deduce, we have to prove that that equation is true. So I don't want to start with that equation. I don't want to start with my burden of proof. If we do, it looks as though we're assuming that it's true and doing what philosophers call begging the question, using the conclusion of the thing we're trying to prove as part of trying to prove it. And that is logical fallacy number one. It's probably the most fallacy to which novice authors of proof in mathematics are prone. So this is another habit that I try to break us up in a class like this. And that is, we're trying to prove this equation is true. So the very last thing that we should see in our proof, so I'm going to write that way down here at the bottom, therefore, X star Y star Z is equal to X star Y star Z. And the stuff that comes in between has to justify that fact. So I'm going to kind of write this thing at the end of the proof. I'm going to write a little QED at the end of the proof as well. So I wrote the last line of my proof, I wrote the first line of my proof, and now what comes in between has to actually be the argument for my proof. So let's put that bit in the middle. Now, to prove that an equation is true without begging the question, How we do it is we pick one side of this equation. So let's say I pick this expression on the left-hand side, and then go through a process of iterative simplification of that expression to show how we can transform using properties that we all agree upon, so by citing bylines that we can all agree upon, to transform this expression into that expression without begging the question. So here's what that ends up looking like. So I'm going to put that expression, x star y star z, I'm going to put that on my first line that I'm about to start working with, x star y star z. And then I'm going to start by using the definition of star, so this definition that told me where the star operation even came from in the first place, to do the first half of the work on my napkin. Right? So what that's going to look like is, what are we going to have here? Quantity x plus y plus xy, quantity star z. And then next to that operation, I'm going to put in my citation, by definition of star. So the first line in this manipulation is going to show me that first thing that showed up on my napkin, right? This thing, by definition of star, x star y star z is equal to that. Right? Okay, and then on the next line, I'll do the next simplification that I did on my napkin, where I eliminated the second star. Right? So this is then equal to x plus y plus xy plus z plus x plus y plus xy quantity times z. And again, for the same reason, by definition of star. Ooh, so now we've really got a lot going on as part of our proof. Right? So how these proofs tend to look is we take an expression, we simplify it. It tends to, rather than get simpler, it tends to look like it gets more complicated. And then our job is to try to rein in that complication. So what we're going to do is we're going to, from the end of this simplification, try and figure out how to get to the end of this simplification and then work our way backwards. Okay. So now we're going to take a look at what we have and use the properties of real number arithmetic to, first of all, try and get rid of the parentheses around this part of the expression. Second of all, get rid of these parentheses by using the distributive property. And so when I do that, what I get is going to end up looking like this. X plus y plus xy plus z plus, let's add in some steps here, x plus y plus xy quantity times z. So what I just did here is by associative property of addition in the real numbers. Okay. So let me update my proof here. So if I just wanted to drop the parentheses that we had right here, I needed to know that that dropping of parentheses doesn't matter. And the reason it doesn't matter is that the real numbers have the associative property with the operation of addition. That we can take for granted in our course. It's not something we would prove. It may be something that you prove when you take Introduction to Real Analysis, for example. But I'm including my byline over here on the side to provide the justification, the rationale for why the reader should believe that we can just drop those parentheses. Because as a reader of proof, you're always skeptical, which means that as a writer of proof, you should anticipate that skepticism. And that's what bylines are for. It provides the evidence for the argument that you're making. Let's eliminate the second set of parentheses that are right here. Right? So to do that, we'll use the distributive property of multiplication over addition. That's something that exists in the real numbers as well. By distributive property, let's just say distributive property of multiplication over addition. I don't have a ton of room here to spell out more of that. So now we've completely arrived at this, this expression that's on my napkin. Now I need to wrap back around, turn that expression into this expression. And all that takes, because all the terms are the same, they're just written in different order, is the commutative property of addition. So we're going to resume, we're going to pick up our story at the bottom of the napkin. X plus y plus z plus yz plus xy plus xz plus xyz. And how we did that is we just rearranged the summands in that sum by the commutative property of addition. That is something that's true in the real numbers. Right? So I got to the halfway point in my napkin, then I jumped down to the bottom of my napkin, and I'm going to work my way back up to this. Okay. What's so awesome about this way of doing it is not just that it's logically consistent, but also that as a reader, you get to look, well, as an author, let's say, as the author of this proof, you get to look brilliant when the reader reads this and says, wow, it was rearranging the terms at this step was exactly the right thing that the author wanted to do, because it got them exactly to the answer that they were trying to get to. Because now what are we going to do? We're going to take these three terms right here, and we're going to try and factor out the x, which we can do again by the distributive property of multiplication over addition. So at that stage, we have x plus y plus z plus yz plus x times the quantity y plus z plus yz. All right? And we'll put the citation again by the distributive property of multiplication over addition that exists in the real numbers we're taking for granted. Right? So I just factored the x out right here. And at the next step, what I want to do is add in a new set of parentheses. And that new set of parentheses I want to put around x plus z plus yz. Right? So again, y plus z plus yz, that's a quantity that I want to turn into y star z at the end of the day. So I want to put in a new set of parentheses around that, which I can do by the associative property of addition. Whoops, I missed my parenthesis. Not quite in the right place there. And I managed to gobble up a z that I didn't want to gobble up in the process. There we go. Okay. And now is when we get to look super smart, because y plus z plus yz is what we call y star z. Right? And so we have x plus y star z plus x times y star z. And here we're just using by definition of the star operation. And already I'm starting to run out of room on the page here. Let me take a moment and just do the old trick of shrinking your font size. Hopefully that will buy me a little bit of space here. Sorry, I'm just trying to get back to good here, and I've got a bit of a problem with my syntax. That's all right, we'll fix this at the end. Okay, but then now, again, I'm looking at this, and I have x plus blah plus x times blah. So it's the sum of x and this plus the product of x and this. So again, using the definition of star, we're taking now our last step back from this expression to that expression. And that gets us x star, the quantity y star z. Again, that's by the definition of the star operation. So we just unraveled this calculation that we did on a napkin into a very long string of calculations here in my proof, right? But that was the string that was necessary, and it's a bit heavy-handed, but I wanted us to really dwell on it this time because it's important here that each one of the steps that we took was, if we wanted to be really logically airtight, necessary. And at each step we had to appeal either to the definition of star or to an arithmetic property of the real numbers that we're going to take for granted for the sake of our course. So all of this stuff was necessary to get us to the end of the proof. But again, we took care to remind the reader what the burden of proof was at the very outset. We wish to show that x star y star z is equal to x star y star z, right? We stated the burden of proof. And now that we have shown by a long string of byline arguments that in fact the expression on the left side of this equation is equal to the expression on the right side of this equation, and that this is true regardless of which x, y, and z the universe chose for us, right? So the first thing we did is we eliminated that universal quantifier by saying let x, y, and z be arbitrarily chosen. I actually want to add those words in here because we usually stress those and I forgot. Okay. We let the universe arbitrarily choose those x, y, and z, And then we wish to show that x star y star z is equal to x star y star z. We stated clearly what the burden of proof was. And then this work, which we engineered from the scratch work that we had on our napkin, that's how we actually demonstrate that this equation does in fact hold. Then we remind the reader that that was exactly our burden of proof. And maybe I'll remind the reader once again that we had eliminated a universal quantifier. So for any such x, y, z. And that concludes our proof. So this was a very long-winded explanation of this, but I hope it was valuable because when we want to show that a property like the associative property holds in general, this is what those proofs tend to look like. We do some computations on the backside of a napkin to verify that the proof is actually going to work out. And then when we go to write the proof, we go back through all of the individual steps that we would have to have done in order to establish that that proof was true. So let me pause here for about 30 or so seconds. If you're watching this live and have questions about the proof that we just did that you didn't get a chance to ask, now is a good time. But then after that, we are going to move forward into our next set of proofs. First of all, is every group of 6 elements abelian? Prove or disprove. And then second of all, what, if anything, can we say about the power of a conjugate of an element? So that's where I want to go next after we take a quick break. I need some elevator music or something. I don't have anything ready today. My coffee's getting cold. I'm talking too much. All right, let's move forward into our next exercise. The next exercise asks to either supply a proof or a counterexample for the assertion that groups of 6 elements must or might not be abelian. So this is the kind of question that group theorists, abstract algebraists, absolutely love, right? It's a question that's really sort of open-ended, and it gets to the heart of what we try to do as algebraists, which is to classify structure. So let's think about what this question is actually asking us to do. Prove or disprove that every group containing 6 elements is abelian. So the absolute brute force way of approaching a problem like this would be to just kind of, say, let's suppose that G is a group that has 6 elements in it. And so we'll give those elements names. Because we know, based on the properties that every group has, that groups have to have a identity element, and that identity element is unique, let's call the identity element E. And then let's give all the other non-identity elements names, A, B, C, D, and F, or something like that. So let's let these 6 things be the 6 elements in my group. And if we're really being naive, if we don't want to use any specialized knowledge at this point, what we would probably do is try to write down a multiplication table, or since this is a group, we can actually call it a Cayley table. E, A, B, C, D, F. E, A, B, C, D, F. And just try to write out a times table for this thing. Well, if E is the identity element, then we know for sure that the first row and the first column are just going to be repetitions of the first row and the first column. So one of the first things we learned about multiplication tables is how to spot the identity. So we know what those rows and columns have to be. But then where we go from there is a really open-ended question, right? And there's, a ton of different ways, a finite but large finite number of different ways that we can fill in the rest of our table. But we know that a few things have to be true of the ways in which we fill in the rest of our table. So the multiplication table for a group is called a Cayley table. So Cayley table is just a fancy name for multiplication table. But we know for sure that some things have to be true. That because of the identity property, we have to have this, this row and column of the identity, row and column of E, are the same as the first row and column of the table. Right, they just have to be repetitions. We also have the inverse property. And the way to interpret the inverse property is that given any element, let's say C, for example, in my group, there has to be some other element, or maybe it's C itself, which when I multiply C by that thing is going to give me the identity element in my group. In other words, if I look on the same row as C, I have to find my identity element somewhere on that row. Same thing on the column of C. The identity element has to be somewhere in the column of C as well. So E must show up in every row and every column. There can't be a column that doesn't have the identity element in it, right? Because if there were, that would mean that there's no way to turn a certain element into the identity by multiplying it by its inverse. We also have the closure property. And the closure property just says that there can't be any new elements inside the table. Every entry inside my table has to be one of the elements from the first row and the first column. Right? I can't suddenly like decide to write in a Q in here or something like that, because then we wouldn't have the closure property. But the other underrated thing is that we also have other properties of groups that we studied in this chapter, one of them being cancellation. So this is a good opportunity for me to quickly mention, there was a question in class we didn't quite get to the other day asked by one of your groups, which was, what does the cancellation property tell us? This came from one of the daily works about the Cayley table, or the multiplication table for a group. So here's an example. Let's suppose that we had some element, let's say D, and suppose that that element showed up in two different spots on the same row of my multiplication table. Right? So let's suppose that D shows up in two different places on the same row. What would that mean? Well, that would mean that there are two different ways to multiply B by something and get D. So BA would be equal to D. And then conversely, BC would also be equal to D. Right? So we would have this equation would be true if D showed up in both of these places on a Cayley table. But that would mean that BA and BC are equal to one another. But we know that every group has both the left cancellation property and the right cancellation property. And in this example, because my group has the left cancellation property, we could cancel the B's from both sides and find out that A, in fact, is equal to C. And that would come as a surprise to us, because we decided that our group has 6 elements in it, right? And that, therefore that A is, by assumption, a different element than C. So what this means is that we can't actually have the same element appear in two places on the same row. So no repeat elements in any row because of the left cancellation property. But then the right cancellation property would imply that we also can't have any repeat elements in any column. Right? And so that actually constrains how we can write a Cayley table for a group in a way that's probably a more interesting constraint even than the other group properties that we talked about here. What this implies is that Cayley tables are what are called Latin squares in mathematics. A Latin square is just a square array of numbers or symbols in which no element is repeated on any row and no element is repeated on any column. It's kind of like there's a relationship between Latin squares and Sudoku. If we're trying to write down a Cayley table for a group, it's like we're taking the elements in my group and making a Sudoku table out of them. The only difference with Sudoku is that there's more structure in Sudoku. There's also those little 3x3 squares inside of a Sudoku that also can't have any repetition. There's no such restriction in group theory. But the theory of Latin squares is very well studied mathematically in combinatorics. How many different Latin squares can we make with a given set of numbers? That's an interesting counting problem. So every Cayley table is in fact a Latin square. But not every Latin square turns out to be a Cayley table because of these properties, for one, and also because of one more. And this is the hardest one to quantify. It's the associative property. I know I said earlier in our stream that associativity is also generally something that we don't worry about whether it's true, because it usually is. The one time we should worry about it the most is if somebody is just randomly trying to sell you on a Cayley table for a group, because the associative property is hard to prove using a Cayley table, with a Cayley table. Because a Cayley table is only ever showing us the product of 2 elements at a time, and the associative property needs us to look at 3 at a time. Whoops, 3 at a time. Hands are not working for me today. It's easier to disprove the associative property by finding one counterexample. You can generally use a Cayley table to do that. But to actually prove associativity using a Cayley table, there you're really stuck if the Cayley table is the only thing that you know. Because generally, to prove the associative property, we really do need to make a general argument like the one that we did earlier in this video. Okay, so can we use a Cayley table to prove or disprove that every group of 6 elements is abelian? I wouldn't recommend doing it. I think what the author of this problem, so when Judson wrote this problem, what he had in mind for us to do is to think about, just think of the examples of groups that we know. Think of examples of groups that we know up to this point that have 6 elements in it. So one example of a group with 6 elements in it would just be the group of integers with the addition operation happening modulo 6. This is a kind of group with which we are going to get very familiar this semester, with addition mod 6. And I'm putting brackets around these integers just to remind us that what we're adding here are really not integers, but they're integer equivalence classes, modulo 6. Usually we end up dropping those brackets later on in the semester, but for now I'm going to keep them because Judson keeps them at this stage in the game. So this is a group that has 6 elements in it. It's like a clock face that has the hours 0 through 5 around it, and we use addition, right, to move around that clock. That's an example of a group that has 6 elements in it. Is that group abelian? Well, yes it is, right? Because the addition of integers is a commutative operation, and that commutativity descends to addition modulo 6 as well. So if the question is to prove or disprove that every group of 6 elements is abelian, this is not really giving us evidence to disbelieve, but it's also not giving us enough evidence to prove that every group of 6 elements has to be abelian. So what the author has in mind is for us to keep thinking of more examples. And there's one more example of groups that we've seen so far that has 6 elements in it. And that is the group of symmetries of an isosceles triangle. ER, R squared, T, TR, and TR squared. That is a group that has 6 elements in it. And the operation is composition of symmetries, which is a function composition operation. Right? This is the group that we call the dihedral group of the triangle. I call it D3. So this is a dihedral group of the triangle. Is this an abelian group? And that's something that you should jump at right away, because we studied when we first met this as a multiplication table. We were using our we were using an app to actually investigate. Let me pull the app up again real quick here, if I remember the address. Dihedral Scratch. I think that's the right one. Yeah, there we go. So when we first met this example, we were playing around with this app, right? And all of the elements in this group are just the symmetries of this triangle. But you were able to figure out that T followed by R, for example, gives me a symmetry of this equilateral triangle that's actually different from R followed by T. Okay. So TR is not equal to RT inside of this group. And what that tells me is that the operation in the dihedral group of the triangle is not, in fact, commutative. TR gives me a different configuration of the triangle than RT did. Right? And therefore, this group, the dihedral group of the triangle, is not an abelian group. And so now that actually gives me sufficient evidence to answer this question. Prove or disprove, is every group of 6 elements abelian? Well, this is a counterexample. There does in fact exist a group of 6 elements that is not abelian, namely the dihedral group of the triangle. D3 is not abelian. Of course, this doesn't tell us whether this is the only example of a group of 6 elements that's not abelian, but the question didn't really ask us to go that far, right? Is it true that every group of 6 elements is abelian? No, it is not true. But of course, replacing the number 6 here with something else gives us a totally new question. And one of the more exciting questions that we're going to be able to answer in the first half of this semester relates to a large number of different possibilities for what we could put there. Let's wrap up our stream today by looking at this last question about the power of the conjugate of an element. What does that end up looking like? So this problem is problem number 25 in Judson's exercise set. And so the problem says, let A and B be elements in a group G. Prove that A times the nth power of B times the inverse of A is equal to the nth power of A times B times A inverse for any integer n. So the first thing that I notice about the statement of this thing that we're supposed to try to prove is that it's a statement that's quantified on all of the integers, all integers n. And so what that does for me is it kind of suggests that we may end up using mathematical induction as part of our toolkit for actually succeeding in this proof. We might need to, we might not need to, but we'll kind of see. We'll feel our way into it. So again, I want to write this proof down on a napkin, and then together, we'll quickly, this will be actually a quicker proof than the first one that we did, try to write it up as a formal proof. So the first thing that I want to mention is just a bit of terminology, because it's terminology that I want to come back to over the course of this semester. You don't need to know this, but I'm going to use this word a lot. So we call A, B, A inverse a conjugation. You may have seen conjugation in your linear algebra class last semester. Conjugation is one of the things that we do in linear algebra as a way of changing the basis for a linear transformation. That you might have seen matrix products that look like this. So that's the conjugation of B by A. So when I conjugate B by A, what I do is I multiply on the left by A and on the right by the inverse of that same A. So you're just kind of hugging the element in the middle by another element and its inverse, right? So that's what we call conjugation. All right, so let's get out a napkin once again and see if we can sketch out the computational part of this proof, and then figure out how to present the proof in the fullness of its logic. All right, so if I look at this equation is our burden of proof, and the value of n needs to be, again, for n and z. So there's an implicit word for all n and z, or for any n and z. So just like in our first proof, the logical structure that we have includes this universal quantifier. For all n integers, we have a times b to the n times a inverse must equal a b a inverse quantity to the n. So just like in our proof of associativity, on my napkin, I'm going to take one of these expressions and try to simplify it out to the extent that I can. A b a inverse quantity to the nth power. How can I simplify this out? Well, because n is an unknown, we don't know how many powers of this quantity we're trying to take at this point. Let's just sort of use some, dots to draw this out. So a b a inverse times a b a inverse. I'm going to pretend, first of all, that n is positive, and then sort of write out what this product ends up looking like. Right? So this is what it is. It's a b a inverse in parentheses repeated a whole bunch of times. right? And the number of times that it needs to be repeated ultimately is n. Let me sort of sketch that in here. Just don't want to lose the thread here. So we've written that out n times. Okay, but then when I look at this observation, what do I notice? I notice that, first of all, we have a lot of parentheses that we actually don't need because of the associative property that holds in every group. So this is, again, why we want the associative property in our algebraic system, so that we can just get rid of all these parentheses. And then we can do all of these evaluations in whatever order we like. ABA inverse, ABA inverse. So parentheses aren't doing anything for us. ABA inverse. So we'll just get rid of them by the associative property. But now what happens? Now I've gotten some A inverses next door to some of my A's. And that's good news, because the inverse property of every group means that that just turns into the identity element in my group. And the identity property in my group therefore tells me that whether I write that identity element or whether I don't write that identity element, the result is the same. And so I can just, quote unquote, cancel that product of an A inverse with an A. And so what I get is A, B, skip B. And then this A inverse is going to cancel with the next A that's sitting next to it. So that thing will have canceled. This last A here will have canceled with the A inverse in front of it. And so what we anticipate is that the only things that are left in the middle here are a bunch of B's and then an A inverse at the very end. So that's all happening either in my mind or on a napkin or something. So I'm kind of saying the key observation is that all these A inverse A's in the middle are going to wipe themselves out. And now all we have left is a bunch of B's. How many B's do we have? Well, we're going to have had one for each of the original factors that we had, of which there were n. And so this will end up being b to the power n. And so that gets us exactly to the other expression that we were trying to get to here. So this is what happens on a napkin, right? If you hand it in for me to review, right? Chances are I'm going to look at that and say, this looks good, but it's not a proof, right? In a proof, we actually have to communicate the logic and not just the computation behind what was just done. And so if I were to write this up as a proof, let's keep that on the screen. Let's go to a new page, and I'm going to start writing out my proposition. So the proposition is that if G is a group and A and B are elements of G, or maybe I'll say it this way, let G be a group and A and B be elements of G. Let G be a group and A and B be elements of G. If n is an integer, then A times B to the n times A inverse is equal to the quantity A, B, A inverse to the power n. All right, so let's get that up on the screen here. That's now the proposition that we're going to try to write a proof of. And here it is. Right, so that's the thing that I want to prove. And I want to have my napkin alongside me so that to sort of guide our steps here. I got one too many parentheses. Sorry about that. Okay, so we'll start in on our proof. So again, just like before, we've got an if-then. So I want to always try to frame the things that I'm trying to prove as ifs-thens, so that we can then indicate to the reader what our strategy is going to be. But what we'll notice from the work on our napkin is that it kind of matters, it's going to matter in my proof, what value n takes. In particular, I sort of made the assumption here that n was a positive integer, right? Because if n were a negative integer, it wouldn't be the same to take the nth power to take the nth power to mean I'm just multiplying this thing by itself n times. So probably we need a mathematical induction argument here. So I don't want to actually go through the whole bits of it here. Let me just, let's just do the piece of the proof which would be for positive values of n. And then the second case will be for the negative values. So for that, I'm going to indicate to the reader that I'm splitting this into two cases. Case 1, if assume n is a positive integer. Now we can use the argument that we wrote down on our napkin. So we will show, and again I'm going to use by mathematical induction. So there I'm signaling to the reader my strategy, that this equation holds true. Copy and paste that equation. But now by writing that in my proof, I've also committed the sin of not having surprise symbols, right? I've got surprise symbols now. A and B are surprise symbols. We know what n is, but we don't know what A and B are. So that I want to put front-loaded at the beginning of my proof. And I'm going to do that just by repeating the first line of the proposition. Let G be a group, and A and B be elements of G chosen arbitrarily. Right? Now, case 1, assume that n is a positive integer. We're going to show by mathematical induction that this equation holds. So again, I've signaled the strategy, and I've signaled what the burden of proof is for my argument right here. So now to do it, we'll use mathematical induction. My base case for the induction on n being positive integers will be the case when n is equal to 1. But then when n is equal to 1, this equation just becomes a times b to the 1 times a inverse equals a times b times a inverse. And that's the same thing as the quantity a times b times a inverse to the first power. And we are done. So the base case of this induction, there's not a whole lot to do. When I substitute 1 for n, it's sort of patently evident why the left-hand side of this equation agrees with the right-hand side of this equation. Because raising something to the first power just gives us itself. So now, to complete the induction, we continue by making the induction hypothesis. And in our induction hypothesis, we assume, this is the place where we definitely want to use the word assume, assume that for a specific value of this integer n, that our equation holds. And rather than use n here, I'm going to use k, just to avoid us confusing the argument. Assume that for a given value of k, or for a given positive integer k, we have that this equation holds with a k in that place. So assume that this is true. This is going to be something that we now want to use as part of our argument. And so now, the inductive step, we're going to state the new burden of proof. Right? The new burden of proof, we wish to show that this statement is true not for k, but for k plus 1. K plus 1. A inverse is equal to AB A inverse to the power k plus 1. So my burden of proof has shifted, right? I'm now telling the reader we have a new burden of proof because we're using an induction, and now what we need to establish is this equation, assuming the previous equation. So let's go ahead and adapt the work that we have on our napkin to be exactly what we wanted there. So I'm going to write this piece of the argument up here instead. So I now want to prove this equation, a b to the k plus 1 a inverse equals ab a inverse to the k plus 1. And so for that, I'm going to start with the expression on the left-hand side, the right-hand side, a b a inverse quantity to the k plus 1. And because I'm writing an induction proof, my goal is to set myself up to use the induction hypothesis. And the induction hypothesis, which we're assuming to be true, has k's in the exponents instead of k plus 1s. So my strategy has got to be to reduce this exponent from k plus 1 down to k. I can do that by just peeling off 1 power of AB A inverse. So AB A inverse to the k times AB A inverse. Right? I think we can all agree that taking the k plus first power of something is the same as taking the kth power and multiplying it by the first power. Right? Because of the properties of exponents, we can just add those exponents back. But why this is valuable is that this factor, A inverse to the power k, is a factor which our induction hypothesis, which we are assuming to be true, tells us how to simplify. That that's equal to a times b to the k times A inverse. And that's the magic. Right? A times b to the k times A inverse. That's the application of our induction hypothesis. Then I've got A inverse sitting over here on this side. But now you can see what happens, right? This is where the observations that we made on the napkin come in. The associative property, letting me ditch these parentheses. And then the magic cancellation that happens with the adjacent A inverse A. Right? So that cancellation happens right here. And from there, now we can see what's happened. The only thing left is A times b to the k times b times A inverse. So I have an A at the beginning, I have an A inverse at the end, and then I have b to the k times b, in other words, b to the k plus 1 on the inside. And that's exactly what I was trying to get in my new burden of proof. So that's the magic of induction. The induction avoids us writing this sort of dot, 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 hand-wavy, everything in the middle cancels kind of argument. That stuff happens on your napkin. In your proof, we actually have to be careful and systematic. And this is why the principle of mathematical induction exists, is to help us be concrete and specific about this part of the argument. So now let's embark upon that piece. So again, just like in our last example of writing down a proof, our burden of proof is this equation. So I can't write this equation down. If I write it down as part of my reasoning, and it looks like I'm assuming that it's true and therefore begging the question, and that's the #1 logical fallacy for proof writers to avoid. So instead, I again want to work from one side of this expression to discover the other. And now is when I'll use the argument that's directly above, it's directly above the screen right here. So we'll start with the right-hand side, A inverse to the power k plus 1. And the first thing that we did there is just peel off 1 power of A inverse. And that is just algebra. It's just properties of exponents, which maybe we'll cite this time around, but generally, you know, I don't need you to cite this absolutely every time. A inverse. By properties of exponents. So there's the first line of our argument, right? We're peeling off that 1 power. And then at the next stage, we applied the induction hypothesis. That was the magic sauce, right? That was how we got from the k being outside the parentheses to the k landing inside the parentheses on top of my b. We used exactly the induction hypothesis to do that. A times b to the k times A inverse. So we just simplified that first factor. And then I have quantity A inverse, once again, by the induction hypothesis. And I'm going to put an exclamation point there. Probably don't need that exclamation point as the author of a proof, but I think that's exciting. And that's also how you know that you needed induction in this argument. If you're not actually explicitly using your induction hypothesis, then you're probably not actually writing a proof by induction. So here we explicitly applied the induction hypothesis. And so we know that induction was a necessary part of the argument that we're making. Now we removed these parentheses. And we remove those parentheses using the associative property, A times b to the k times A inverse times A times b times A inverse. A b to the k, A inverse, A b, A inverse. Again, that's a step that you might not always need to write down. But I'm going to say it here explicitly because we're still paying close attention to the properties of groups. And the fact that G is a group means that the associative property holds for the operation in G, which means I can ditch those parentheses. It also means that on the next line, I can cancel the A with the A inverse that's sitting right here in the middle, right? And so when I cancel that, I get A b to the k times E times B times A inverse. And again, later on down the line, we're not going to be as explicit about those steps, but let's be explicit now by the inverse property in G. because G is a group, it has the inverse property, and so A inverse times A is equal to the identity element E. And then we can get rid of that E using the identity property. A, B to the K, B, A inverse. By the identity property. Because G is a group, we know it has the identity property. And so we get that. But then, B to the K times B can be written as B to the K plus 1. And that's just, once again, by the properties of exponents. Properties of exponents also hold in every single group. And then finally, that actually is exactly the expression that's on the left-hand side of my burden of proof statement. Right? My burden of proof statement was right here. And now I've shown the reader why the right-hand expression in that equation is indeed equal to the left-hand side, left-hand expression in that equation. And so we are ready then to finish our proof. So, by the principle of mathematical induction, how do we say it? Our statement is true for all positive integers of n. So now we're regressing back to the original burden of proof. We needed to show that this is true for all values of n. Our result holds. Whoops. All positive integers n. There we go. So that gives us the case when n is a positive integer. I'm going to leave to the viewer, I suppose, what you would do in the cases where n is a negative integer. The hint that I'll give you there is that the shoes and socks principle for taking the inverse of a product can connect you directly back to the argument that we did right here. So once again, we were being very careful and explicit with all of these steps to sort of write them all out and make sure that they all made it onto the page. You probably don't have to do that in absolutely every case once we get some more expertise under our belt with the writing of proofs. But again, particularly now when we're especially concerned about the properties of groups and the structuring of careful proofs, I want to put all of that, all those steps out there on the table. So that's going to conclude today's live stream. I hope that it was helpful. This video is going to go up onto YouTube, and so you can use the timestamps in the video to jump back and forth between these various problems that we just solved. And I look forward to doing this again on a more regular basis as we move out through the semester. I hope you enjoyed, and let me know if you have other questions or comments. Either drop them in the Twitch chat if you're not my student, drop them in the Doctor's Office channel on Slack if you are, or make comments on the YouTube video, because all of those get to me one way or the other. I hope you enjoyed, and I'll see you next time around.